Hello my curious friend, and a very warm welcome to Deepfield Channel. Tonight, we will venture into one of the strangest and most unsettling places known to physics, a threshold where space folds back upon itself, where time loses the meaning it has always held for you, and where the laws governing everything around you reach their most extreme limit. We will carefully and calmly approach the edge of a black hole, and then we will take a step beyond. I promise to try not to make the subject so fascinating that it drives sleep away, but I must be honest with you, it is quite a challenge. Before we dive into this cosmic abyss, I would love to know in the comments which corner of the world you're listening to me from tonight. And if laziness is already setting in before we even begin, a simple hello will do. That small gesture makes a huge difference, because it shows the platform that this is a welcoming place, and it helps us bring more tired minds to relax and explore with us. If you appreciate our journeys through science, please leave a like and subscribe to the channel, and to those who are already part of this community, my heartfelt thanks. If you wish to get even closer, consider becoming a channel member. Members get early access to videos before anyone else. The link is in the description. Now, wherever you are, find a truly comfortable position. Let your shoulders drop. Allow your breathing to become slower and deeper. If sleep comes along the way, accept the invitation without guilt. Let us begin. There is a boundary in the universe that is not made of matter. You cannot touch it. You cannot see it directly. And if you were ever to cross it, you would feel nothing at the exact moment it happened. And yet, upon crossing it, everything would change forever. This boundary has a name that sounds almost philosophical, the event horizon. And what lies on the other side of this invisible line is one of the most profound questions humanity has ever asked, not because it is hard to calculate, but because it is difficult to imagine, to feel, to fit into anything you have ever experienced. Think for a moment about something simple. Think of a stone thrown into the air. You know, without needing to think about it, that it will come back down. Gravity pulls it back to the ground, and the harder you throw it, the higher it goes, but it always returns. Now imagine that you could throw this stone with ever-increasing force, greater and greater, until you reach a point where it simply never comes back. This point exists for Earth, and for any object with mass. It is what we call escape velocity. To completely break free from Earth's gravitational influence, any object needs to reach a speed of roughly 11 kilometers per second. It is an absurd speed for human daily life, but it is finite, it is achievable. Now imagine a region where the escape velocity is not 11 kilometers per second, nor 100, nor 1,000,000. Imagine a region where the speed required to escape exceeds the speed of light itself. And here is the first great surprise, the first moment the universe shows us it was not built to be intuitive. Light is the fastest thing there is. Nothing in the known universe can move faster than it. This means that if the escape velocity of a place is greater than the speed of light, absolutely nothing can leave. Not matter, not energy, not information, not even light itself. This is the definition of a black hole, not a dark object swallowing everything around it like a cosmic vacuum cleaner, but a region of space where the geometry of the universe curves so radically that all possible directions point inward. This dispels one of the greatest popular misconceptions about black holes. They do not actively suck things in around them, as if they were cosmic drains with their own suction. A black hole does not pull any harder than any other object with the same mass. If the Sun were replaced by a black hole of identical mass, Earth would continue orbiting exactly as it does today. The planets would not be swallowed. The difference is that all that mass would be compressed into an incredibly tiny point, and if you got close enough to that point, much closer than you could ever get to the Sun, then gravity would become irresistible. The issue is not that black holes are more voracious. The issue is that they are smaller, and gravity depends on distance. When you compress a star into something minuscule, you can get much closer before being destroyed. The word compressed here needs to be felt in its full extent. A star like the Sun has a radius of about 700,000 kilometers. If you could compress it until it turned into a black hole, it would fit into a sphere with a radius of roughly 3 kilometers. All that mass, all that substance, the entire volume of something larger than 1,000,000 Earths, concentrated into something smaller than a small town. And at the center of this compressed volume, at least according to the equations we have today, matter itself continues to compress endlessly, reaching a point where density becomes mathematically infinite. This point has a name, the singularity. But the singularity is for later. For now, let us carefully approach the edge. The event horizon is the name we give to the imaginary spherical surface that marks the point of no return. It is not a wall. There is nothing physical there that you could detect upon crossing it. It is simply the place where the curvature of space becomes so intense that all possible trajectories, all directions anything can take, including the direction light travels, curve inward. It is as if space itself were flowing inward, like a river that gets faster and faster as it approaches a waterfall. Far from the waterfall, you can row back. At some point, the current matches your maximum speed and you remain static. Beyond that point, no matter how hard you row, you are going over the edge. The river analogy is not just poetic, it is mathematically precise. There is a way to describe black holes called Painlevé-Gullstrand coordinates, where space is literally treated as a fluid flowing toward the singularity. At the event horizon, the speed of this spatial flow equals the speed of light. Inside the horizon, the flow is faster than light. Everything that exists inside the horizon is being carried by the very geometry of space toward the center, and there is nothing that can go against this current, because going against it would require exceeding the speed of light. Now, an important detail: the size of the event horizon depends on the mass, and the black holes that exist in the universe cover a range of sizes that defies any attempt at intuitive comparison. There are the so-called stellar black holes, which arise from the death of massive stars with horizons ranging from a few kilometers to a few dozen kilometers in radius. There are intermediate mass black holes, still poorly understood, which might have horizons of hundreds or thousands of kilometers. And there are supermassive black holes, which reside at the centers of almost all the large galaxies we know, with horizons that can have radii of tens of billions of kilometers. The black hole at the center of our own galaxy, the Milky Way, called Sagittarius A star, has a mass of about 4 million times that of the Sun. The event horizon of Sagittarius A star would fit comfortably within the orbit of Mercury, and then there is the opposite extreme. M87 star, the black hole whose image was first captured in 2019 by the Event Horizon Telescope, has a mass of about 6.5 billion times that of the Sun. Its event horizon has a radius larger than the distance between the Sun and Pluto. If you were to replace the Sun with this black hole, the event horizon would extend far beyond our solar system. Saturn, Uranus, Neptune, everything would be inside the horizon. This has a surprising consequence. In a supermassive black hole, the average density inside the event horizon can be less than the density of water. The gravity at the surface of the horizon, which physicists call the gravitational tide, can be relatively gentle. An observer falling freely toward M87 star would feel nothing special when crossing the horizon. No wall, no shock, no sensation of a boundary. Just the quiet continuity of free fall. And yet, without realizing it, they would be on the inside, in a territory from which there is no exit. For smaller black holes, the story is different and much less kind. Tidal forces, differences in gravitational intensity between nearby parts of the same object, can be devastating long before reaching the horizon. A human approaching a stellar black hole would be stretched like pasta, a process physicists call, with a mix of precision and humor, spaghettification. Gravity would pull the feet with much more force than the head, and the result would be a continuous and catastrophic elongation. In a supermassive black hole, this difference is much smaller on a human scale, and the fall inward could be, at least for a while, relatively peaceful. But what exactly does it mean to be inside the horizon? This is the question physicists have debated, calculated, and imagined for over a century, ever since Karl Schwarzschild, working in the trenches of the First World War in 1915, found the first exact solution to Einstein's equations for general relativity and discovered, with some unease, that his equations seemed to allow the existence of objects with these extraordinary properties. Schwarzschild sent his calculations to Einstein by letter. Einstein was impressed, but also uncomfortable. For decades, most physicists believed these mathematical solutions were mere curiosities, artifacts of an idealized model that would never materialize in nature. They were wrong, and nature, as it often does, was far bolder than anyone had imagined. Today we know that black holes are not just possible, they are common. They exist in absurd quantities throughout the observable universe. Every large galaxy seems to have one at its center, and stellar black holes are created regularly, every time a sufficiently massive star reaches the end of its life and its core collapses under its own weight. This collapse in itself is one of the most violent events the universe produces. A massive star spends millions of years converting hydrogen into helium and helium into heavier elements through nuclear fusion in its core. This process releases a colossal amount of energy, and it is this energy that supports the star against its own gravity, like a tense balance between two opposing forces. When the nuclear fuel runs out, this balance breaks, gravity wins. The core collapses in a fraction of a second, going from a volume the size of our Earth to something the size of a city. The resulting shock wave ejects the star's outer layers in an explosion called a supernova, which for a few moments can shine brighter than the entire surrounding galaxy. What remains is a collapsed core. If the mass of this core is large enough, the pressure of the neutrons, the force that would normally prevent a total collapse, is not enough to hold back gravity, and the collapse continues. Matter keeps falling toward the center. The space around it begins to curve increasingly, and at some point, the event horizon forms, emerging from the outside in as the mass compresses, sealing the interior forever. To an outside observer looking past the horizon, something strange would be seen. The collapse would appear to slow down as the surface of the star approached what would become the horizon. This happens because near intense gravitational fields, time flows more slowly. This is not a metaphor either. It is general relativity, confirmed experimentally with extremely high precision. A clock near an intense gravitational field ticks slower than a distant clock. To an external observer, the surface of the collapsing star would seem to become slower and slower, its light increasingly red and faint, asymptotically approaching the horizon, never seeming to cross it. The collapse seen from the outside never seems to complete, but that is the external point of view. From the perspective of someone falling with the star, the collapse is completed in a very short time. The horizon forms, the interior exists, and on the other side something that no equation can fully describe awaits us, like a question the universe asks itself in silence, in no rush to answer. Everything we have just described, the curvature, the horizon, the collapse, the spaghettification, the relativity of time, all of this is the consequence of a single thing. The energy contained in this region of space is so concentrated that it deforms the very fabric of reality. And this brings us to a question that hangs in the air like smoke after a blown-out candle. Where, after all, does all this energy that animates this system come from? The energy that fuels the collapse, that keeps the horizon where it is, that sustains whatever exists in there? The question about the origin of this energy does not begin in physics textbooks. It begins in a much earlier instant, when someone looks at a campfire and realizes that the fire does not create heat out of nothing. It releases something that was already stored in the wood, waiting to be awakened. Energy does not appear, it transforms. It migrates from one form to another, from one dwelling to another, and each transformation leaves a trace that we can measure, feel, and calculate. The black hole, in this sense, is no different from a campfire. It too does not create energy out of nothing. It inherits it. It concentrates it. And by concentrating it beyond any limit nature normally allows, it reveals something the campfire could never reveal. What happens when gravity wins over everything? The original source of all the energy that sustains a stellar black hole is the same one that sustained the star that birthed it. It is mass. Mass itself, in the deepest sense physics knows, is energy stored in an extraordinarily dense form. It is not a poetic metaphor. It is an equation Einstein wrote at the beginning of the 20th century that forever changed how we understand what things are made of. An amount of mass, even at rest, even without moving, burning, or exploding, carries within it an amount of energy proportional to the square of the speed of light. And the speed of light is such a large number that squaring it turns any mass, no matter how small, into an immeasurable reserve of energy. A stone in the palm of your hand contains more energy, in this sense, than any bomb humanity has ever built. What prevents it from releasing it in this form is simply the fact that there is no process in everyday nature capable of converting mass directly into energy completely. Nuclear fusion, which has fueled the sun for billions of years, converts only a tiny fraction of the involved mass into energy. The rest remains mass, reorganized into different atoms, but even that minuscule fraction is enough to keep a star shining for billions of years. During the life of a massive star, this nuclear fusion is the force that resists gravity. Imagine holding an open umbrella against a very strong wind. The wind wants to close the umbrella, crush the structure, reduce everything to a compact point. Nuclear fusion is the effort of your arms keeping the umbrella open. As long as there is fuel, as long as there is hydrogen to fuse into helium, helium to fuse into carbon, carbon to fuse into increasingly heavier elements, your arms hold up. Radiation pressure and the pressure of the heated gas push outward with the same intensity that gravity pushes inward, and the star remains in equilibrium, suspended in this tension for geological eras. The name for this balance is hydrostatic equilibrium. It is not a state of peace. It is a state of constant war between two equal and opposite forces, waged in silence for billions of years. One of the greatest physicists of the 20th century, Subrahmanyan Chandrasekhar, spent years trying to understand what happens when this balance eventually breaks. He was a young Indian student, travelling by ship from India to England to study at Cambridge, when he realised something disturbing. While the other passengers slept or watched the sea, he did calculations on scraps of paper and concluded that stars above a certain mass limit could not simply shrivel and cool down peacefully after exhausting their fuel. There was a threshold. Below it, a star could become a white dwarf, a dense and stable object supported by a form of quantum pressure called electron degeneracy pressure. Above this threshold, no known force would be able to halt the collapse. Chandrasekhar presented these calculations at a conference in Cambridge and was publicly humiliated by Arthur Eddington, one of the most respected astronomers of the time, who claimed that nature simply would not allow it, that there must be some law, yet undiscovered, that would intervene and save the star from such an absolute fate. Eddington was wrong, and it would take decades for the physics world to formally recognize this, eventually awarding Chandrasekhar the Nobel Prize long after the time when the honor would have been most valuable to him. What Chandrasekhar realized on that ship is that gravity has infinite patience. It never tires. It consumes no fuel. It simply exists as long as there is mass, and it pulls with an intensity proportional to the amount of mass present. As the star collapses, it becomes denser. As it becomes denser, the surface gravity increases. As gravity increases, the collapse accelerates. It is a cycle with no natural break, a process that feeds on itself, like an avalanche gaining speed with every meter of snow it drags along. The law describing this behavior was already known since Newton, but its most complete and precise form was written by Einstein in the General Theory of Relativity. Gravity, according to Einstein, is not a force in the conventional sense. It is a deformation in the geometry of space and time caused by the presence of mass and energy. The greater the mass, the more concentrated it is, the greater the curvature. And moving objects, including light, follow the most natural path available in this deformed geometry, which from the perspective of a distant observer looks like an attraction, a fall toward the mass. This distinction matters enormously for understanding the interior of a black hole. If gravity were just a force, as Newton imagined, it would simply pull things harder as we got closer. But since it is a curvature of space-time itself, there is a point beyond which it is no longer a question of having enough force to escape. It is a question of geometry. The space-time inside the event horizon is so curved that all possible directions, all available paths for any object or signal point inward, toward the center. Not because something actively pushes them, but because the geometry of space no longer offers any way out. It is like being in a river that flows faster than you can swim. No matter how strong your arms are, the current takes you. Karl Schwarzschild was the first to realize this mathematically. He was serving on the Russian front during the First World War, solving Einstein's equations in the pauses between combat, when he found the first exact solution to the field equations. This solution described the space-time geometry around a perfectly spherical, non-rotating mass, and it contained something disturbing, a specific radius proportional to the object's mass, within which the geometry became mathematically strange. The temporal component of the metric changed sign. What was time on the outside became a spatial direction on the inside. What was space on the outside became a temporal direction on the inside. This is not just a mathematical abstraction difficult to visualize. It has concrete and deeply unsettling physical consequences. In our daily lives, we can move back and forth in space. We can choose to go left or right, up or down. But in time, we are forced to move forward. We cannot return to yesterday. The temporal direction is a compulsory one. Well then, inside the event horizon of a black hole, the direction pointing toward the singularity, the center, begins to behave like the temporal direction. It becomes compulsory. It is impossible to stop approaching the singularity for the same reason it is impossible to stop aging. It is not a matter of force or willpower. It is the structure of space-time in operation. Schwarzschild did not live to see his ideas fully recognized. He died a few months after sending his solutions to Einstein, a victim of a disease contracted in the trenches. Einstein was impressed by the work, but he himself did not believe for years that the solution described something that could actually exist in nature. The problematic point, the Schwarzschild radius, was considered for decades a mathematical singularity with no physical meaning, an artifact of the coordinate system, some said, an error to be resolved by a more complete theory, others hoped. It took decades of work by other minds, and a crucial conceptual breakthrough made by David Finkelstein in the mid-20th century, for the physics community to accept that the event horizon is real, that it is not a mathematical aberration, but a physical boundary with observable consequences, and that what Schwarzschild found on the Russian front was, in fact, the mathematical description of an object that bends space-time beyond any return. The fundamental imbalance that makes a black hole exist and persist is precisely the collapse of that war that lasted billions of years, when the nuclear fuel runs out in the most massive star, when iron begins to accumulate in the core and fusion no longer releases enough energy to maintain radiation pressure, the arms holding the umbrella simply give out, and the avalanche begins. The core collapses in a fraction of a second. The rest of the star falls onto it and rebounds in a colossal explosion called a supernova. But if the remaining core is massive enough, not even neutron degeneracy pressure, a quantum resistance even more intense than what Chandrasekhar calculated for electrons, will be able to sustain the weight. And the collapse continues, unstopping, unbraked. With no visible bottom, what remains is not the star. It is the impression it left on spacetime. A curvature that persists even after the mass that caused it has compressed into something the equations describe as a point with no extension. And this curvature, this hole in the geometry of the universe, is self-sustaining because gravity needs no fuel. Once the horizon has formed, once the geometry has reached that threshold, it maintains itself. The mass inside, whatever it may be, continues to curve space-time. The horizon stays where it is. The interior remains inaccessible. Locally, in the moment immediately after crossing the horizon, what an observer in freefall experiences is not dramatic. Tidal forces, that difference in gravity between the head and feet that would eventually cause spaghettification, are minimal at this instant for sufficiently large black holes. The space around seems ordinary for a moment, but the geometry has already changed. The directions have already inverted in the sense we described, and every passing moment inside the horizon inevitably brings the observer closer to the center, not because gravity pushes them harder with each step, but because time itself is flowing in that direction. Every particle that crosses the horizon brings with it its mass, its energy, its momentum. Every particle contributes to the curve of space-time. Every contribution, no matter how small, adds to the collapse that the horizon preserves. It is a mechanism that repeats continuously on a microscopic scale every time anything crosses that invisible boundary. A particle of light, a stray hydrogen atom, a radio wave that passed too close, all of them add to the system, all of them feed the imbalance, and the horizon grows imperceptibly with each addition. What happens when this mechanism repeats, not once, not 1,000 times, but millions and billions of times over cosmological eras, with matter falling, with energy accumulating, with the horizon growing and the interior becoming increasingly distant from everything we know as comprehensible physics, is a question that remains suspended here, like that smoke after a blown-out candle, waiting for the next step of the conversation. When this mechanism repeats over cosmological eras, something extraordinary begins to emerge from the apparent chaos. It is not order imposed from the outside, not an architect organizing the components according to a plan. It is something much more unsettling and much more beautiful. It is order arising from within, order that no individual particle carried with it, order that only appears when the scale becomes large enough and time long enough. Physicists have a technical name for this phenomenon, but the feeling it provokes is that of discovering that nature has its own aesthetic preferences, that the universe, when left to its own devices, tends to organize itself into patterns that any trained eye recognizes as structure. Inside a black hole, this emergent organization begins with something seemingly simple, the distribution of energy and angular momentum. Everything that falls does not fall with the same orientation, does not fall with the same spin, does not fall with the same trajectory. A gas cloud colliding with the event horizon from one direction brings with it a different rotational impulse than gas coming from another angle. And when these impulses add up over eras, when billions of accretions happen and each contributes its share of rotation to the total system, the result is not a random cancellation. The result discovered by statistical mechanics applied to gravitational systems is that rotation is preserved and amplified. The black hole begins to spin, and when it spins, everything changes. The Kerr solution, found by Roy Kerr in 1963, was one of those moments mathematicians describe as a revelation. Kerr was not looking for rotating black holes. He was solving Einstein's field equations for a specific case of axial symmetry, an abstract mathematical condition describing something with symmetry around an axis. When the solution emerged from the equations, it revealed a geometry so different from the Schwarzschild solution that it seemed impossible it described the same phenomenon. But it did. It described a black hole that spins, and by spinning, drags the very fabric of space-time around with it. This drag is called frame dragging, or sometimes the lens-thirring effect in its weaker version, observable in ordinary objects. But around a rotating black hole, the effect is not weak. Space-time literally rotates with the black hole, as if the structure of reality were a viscous fluid being pulled by the rotor of a cosmic machine. There is a region around the event horizon where this drag is so intense that nothing can remain stationary relative to the distant stars. Even travelling at the speed of light in the direction opposite to the rotation, an object would be dragged forward. This region is called the ergosphere, a word containing the Greek root for work, because it is there that energy can be extracted from the very spin of the black hole. The ergosphere is not inside the event horizon. It is a region around it, a transition zone where the drag becomes absolute but where it is still possible to escape if the trajectory is correct. And within this zone, patterns of organization emerge that would not exist in a static black hole. The particles entering the ergosphere follow very specific spiral trajectories, dictated by Kerr geometry. It is not a simple spiral like that of a flat galaxy. It is a three-dimensional spiral, twisted by the rotational drag, flattened at the poles and expanded at the equator. The space inside the ergosphere has a topology that has no direct analogue in our everyday experience. When matter finally crosses the event horizon of a Kerr black hole, it does not encounter the point singularity predicted by the Schwarzschild solution. The interior geometry is fundamentally different. Instead of a singularity at a point, the Kerr solution predicts a ring-shaped singularity, an infinitely thin toroidal structure in the equatorial plane of the black hole. And although singularities are points where physics breaks down, where equations diverge and lose meaning, a ring singularity has geometric properties different from a point singularity. The shape of the final collapse, the organization of extreme density, depends on the rotational history of the entire system. This historical dependence is one of the most fascinating aspects of the interior. The black hole does not just accumulate mass and energy, it accumulates the history of how that mass and energy arrived. Every object that crossed the horizon over cosmological eras contributed not only its substance, but its orientation, its velocity, its angular momentum, and the current state of the interior is an integral of all that history, a kind of compressed memory of everything the system has consumed. The black hole no-hair theorems, developed by John Wheeler and his collaborators in the 60s and 70s of the last century, say that from the outside the black hole appears to have lost all this information, reduced to just three numbers: mass, charge, and angular momentum. But that is only what the exterior sees. The interior, if the interior still preserves anything, is another conversation. The information paradox arises exactly here, in the tension between what Wheeler's theorems say about the apparent simplicity of the black hole and what quantum mechanics demands. Quantum mechanics is inflexible on one point: information cannot be destroyed. Every quantum state of the universe can, in principle, be traced back to the past and projected into the future. No physical transformation, no matter how violent, erases the data. But if everything that enters a black hole appears from the outside as just three numbers, what happened to the specific information of every particle, every photon, every atom that crossed the horizon over eras? This question divided theoretical physics for decades. Stephen Hawking bet that the information was lost. John Preskill bet it was not, and after more than 20 years of debate, Hawking himself admitted in a memorable conference that there were reasons to believe the information escaped in some way, probably encoded in the radiation the black hole emits. Hawking radiation is itself a phenomenon of large-scale emergent organization. It is not something any individual particle plans to emit. It arises from the quantum structure of the vacuum at the edge of the event horizon. The quantum vacuum is not empty. It is filled with pairs of virtual particles that appear and disappear continuously, borrowed and returned to nothingness in a time so short that Heisenberg's uncertainty allows their existence. Around an event horizon, something extraordinary happens to these pairs. One partner falls inside the horizon while the other escapes to the outside. The black hole loses energy to the partner that fell, and the partner that escaped appears as real radiation to the distant observer. The black hole evaporates, imperceptibly slowly for stellar mass black holes, but it evaporates. And as it evaporates, the global pattern of how it consumes and emits energy defines a complete thermodynamics, with temperature, entropy, and even something analogous to the laws of classical thermodynamics. Jacob Bekenstein was the first to suggest, with considerable intellectual courage, that black holes should have entropy proportional to the area of the event horizon. It was an idea too strange for most of his contemporaries. Entropy is a measure of microscopic disorder, of how many distinct configurations a system could have given its observable macroscopic state. For classical systems, like a confined gas, entropy is volumetric. It grows with the number of particles with the available space. But Bekenstein realized that for a black hole, the relevant information seemed to be on the surface, not in the volume. The Bekenstein-Hawking entropy is proportional to the horizon area measured in units of Planck length squared. This means that an event horizon is in some way a surface that carries information, that organizes in its two-dimensional geometry everything the three-dimensional interior represents. This principle, which became known as the holographic principle, was developed by Gerard de Hooft and Leonard Susskind in the following decades, and it suggests something deeply unsettling about the organization of the interior. If all the information of a three-dimensional volume can be encoded on its two-dimensional surface, then the interior of a black hole, whatever that interior may be, is no more informationally rich than its horizon. The horizon is a kind of projection, a complete map of the territory, and the territory, the true interior, can be understood as a three-dimensional realization of something that fundamentally exists in two dimensions. The physics inside the horizon is no deeper than the physics of the horizon. It is just a different language for the same structure. The ADES-CFT correspondence, conjectured by Juan Maldacena in 1997, mathematically formalized this intuition. In a space with a specific negative curvature called anti-de Sitter, a gravitational theory in the interior is mathematically equivalent to a quantum field theory without gravity on the boundary. It is an exact duality. Two completely different descriptions of the same physical system, one with gravity and dimensions, the other without gravity but with all the information preserved. Black holes in ADS space correspond to thermal states in the field theory on the boundary, and the heat, the temperature, the entropy we attribute to the black hole finds a precise translation in terms of quantum entanglement between the parts of the system on the boundary. This correspondence revealed that the large-scale organization of a black hole's interior is neither random nor arbitrary. It is structured by entanglement. The quantum correlations between distinct regions of the system, correlations that persist even when particles are separated by vast distances, literally build the geometry of spacetime. Mark van Ramsdonk wrote a remarkable paper suggesting that if you cut the entanglement between two regions of a quantum state, the spacetime between the corresponding regions would separate, fragment, cease to be connected. Entanglement is the glue of spacetime. Less entanglement means less connected spacetime. No entanglement means disconnected spacetime. What emerges from this view is a picture of the black hole's interior as a network of quantum entanglement that organizes geometric space. Every point in the interior exists because there are adequate quantum correlations sustaining it. The singularity, where the correlations break down, where the geometry collapses, is the place where entanglement becomes infinite or zero, where the network sustaining spacetime can no longer maintain its coherence. And the overall structure, the way the interior organizes itself from the horizon to the singularity, reflects the history of how the entanglement accumulated, how the correlations built up over eras of accretion. The patterns that emerge from this physics are elegant in a way that does not seem accidental. Kerr geometry, the thermodynamics of Bekenstein and Hawking, the holographic principle, the Maldacena correspondence, all point to a system with a surprisingly rich internal organization, surprisingly simple in some aspects and surprisingly profound in others. And this organization would be much harder to decipher, much more opaque to distant observers, much more stable and silent if there were not an ingredient that amplifies the patterns, that makes them visible, that forces them to manifest beyond the horizon, informs the external universe can register. This ingredient is radiation. Not the common light you know, not the heat of a campfire or the glow of an incandescent bulb, but radiation in the broadest and most fundamental sense physics knows. The spontaneous emission of energy by systems possessing temperature, the propagation of disturbances through the fabric of space, the relentless flow of information encoded in photons, in gravitational waves, in particles crossing the vacuum like messengers of processes that happened elsewhere and in other times. Radiation is the amplifier. It is the mechanism by which what happens inside becomes perceptible outside. It is the language the black hole uses to communicate with the universe, even if that communication is whispered, even if it is almost inaudible, even if it takes eras for any distant observer to decipher it. The power of radiation as an amplifier comes precisely from its apparent simplicity. An individual photon carries a ridiculously small amount of energy. A single quantum of light emitted by the surface of a warm object is something so tiny that no instrument can perceive it in isolation without enormous technical difficulty. And yet, when these photons accumulate, when billions and billions of them converge from the same source, they form the most powerful signal the universe produces. Neutron stars spin sending radio pulses that cross tens of thousands of light years and reach Earth with the regularity of a clock. Black holes in the process of accretion shine with a luminosity that surpasses entire galaxies, forming the quasars astronomers detect at distances of billions of light years. The simplicity of each individual quantum hides the collective power of a process that never stops, that never sleeps, that never tires of transmitting. The amplification mechanism begins in the quantum physics of the vacuum. The seemingly empty space is not absolutely empty. It boils with quantum fluctuations, with pairs of virtual particles that arise and annihilate in time intervals so short that quantum mechanics allows them without violating energy conservation. Under normal conditions, these pairs arise together, interact briefly, and disappear together, leaving no trace. But near the event horizon of a black hole, the geometry of space-time does something extraordinary with these pairs. It separates them. One particle of the pair falls beyond the horizon, becoming part of the interior, while the other escapes to infinity. And since the total energy of the system must be conserved, the escaping particle carries real energy the black hole pays by borrowing from its own gravitational mass. The result is a constant flow of real particles leaving the horizon, an extremely faint thermal glow that Stephen Hawking calculated mathematically in 1974, and that has borne his name ever since. Hawking radiation is cold, immensely cold for any black hole we can imagine arising from a collapsed star. The Hawking temperature of a black hole with the mass of the Sun would be approximately 60 nanokelvins, a microscopic fraction of a Kelvin, much colder than the cosmic microwave background that fills the universe with a temperature of about 2.7 kelvins. This means that in practice, a stellar black hole absorbs more radiation from the cosmic background than it emits, making its evaporation not only slow, but effectively non-existent in the current universe. To detect Hawking radiation from a real black hole, we would need a black hole with much less mass than any asteroid, an object so tiny that we know of no natural mechanism that produces it in abundance in the contemporary cosmos. But the theoretical importance of Hawking radiation does not lie in its immediate detectability. It lies in its conceptual significance. It proves, within the formalism of quantum field theory and curved spacetime, that black holes are not eternal objects. They possess temperature, and everything that possesses temperature radiates, and everything that radiates loses energy, and everything that loses energy eventually runs out. The evaporation time of a black hole with the mass of the Sun would be of an unimaginable magnitude, a number with more than 65 zeros when expressed in years, a time interval that makes the current age of the universe seem like a blink of an eye. But the point is not how long it takes. The point is that it happens. The point is that the interior, with all its rich, entangled and holographic structure, with all its Kerr geometry and Bekenstein thermodynamics, is slowly being translated into radiation, into thermal photons escaping and carrying the information back to the external universe. Beyond Hawking radiation, the most powerful and immediately observable manifestation of the processes happening around a black hole is the accretion disk. When matter falls toward the horizon, it rarely falls in a straight line. It almost always possesses angular momentum, a tendency to rotate inherited from the dynamics of the system it belongs to, and when a rotating cloud of gas begins to spiral toward the horizon, it does not collapse immediately. It forms a flattened structure, a disk spinning progressively faster the closer it gets to the horizon. The internal friction between the layers of this disk, what astrophysicists call turbulent viscosity, and which originates in the entanglement of magnetic fields in the plasma, converts orbital energy into heat, and this heat is radiated. The temperatures in the accretion disk of a stellar mass black hole can reach tens of millions of kelvins in the innermost regions, near what is called the innermost stable circular orbit. This temperature produces emission in the X-ray range, and that is exactly why the first black holes were identified as intense X-ray sources in binary systems, where a normal star transfers mass to an invisible companion. The source Cygnus X1, discovered in the 60s and confirmed as a stellar mass black hole in the following decades, is the classic example. What we see as intense and variable X-rays is the accretion disk screaming, converting orbital momentum and gravitational energy into radiation at a rate that can exceed solar luminosity by a factor of many hundreds of thousands. For supermassive black holes at the center of active galaxies, the scale is completely different, but the mechanism is the same. The accretion disk of a quasar involves gas masses equivalent to many stars, extending over distances we measure in light days or light weeks, and the total luminosity can exceed the luminosity of the entire host galaxy by a factor of 100 or 1,000. These are the most luminous objects in the observable universe, visible at distances representing more than 90% of the extent of the observable cosmos. And all this extraordinary brightness comes from a gravitational process, from the conversion of gravitational potential energy into radiation with an efficiency that no nuclear fusion can match. Nuclear fusion converts less than 1% of mass into energy. Disk accretion around a rotating black hole can convert up to 42% of mass into pure energy, an efficiency that makes any human engine look like a primitive mechanism. There is yet a third manifestation, perhaps the most spectacular of all in visual terms, relativistic jets. In many highly energetic accretion systems, two collimated beams of plasma and magnetic fields are launched perpendicular to the accretion disk in opposite directions, with speeds that can reach 99.9% of the speed of light. The exact origin of the jets is still debated, but the main mechanism favoured by most models involves the Blandford-Zanayak process, in which magnetic field lines rooted in the disk twist around the rotating black hole, creating a helical spiral that launches particles away like a cosmic catapult. These jets can extend for hundreds of thousands of light years, far beyond the limits of the host galaxy, depositing energy into the intergalactic medium and structuring the environment on scales that defy imagination. The galaxy Messier 87, whose central black hole image was captured by the Event Horizon Telescope in 2019, possesses a jet that extends for about 5,000 light-years and is visible at wavelengths ranging from radio to gamma rays. The black hole feeding this jet has a mass equivalent to about 6.5 billion solar masses, and its event horizon, the boundary within which nothing can escape, has a radius of approximately 19 billion kilometers. The image the world saw showed a bright ring of heated plasma and a dark center. The shadow of the horizon, the mark of the absence of light, the fingerprint of the interior upon the exterior. It was the first time humanity saw, with real instruments and real data, the boundary between what can be known and what cannot. These manifestations do not exist only in the distant cosmos. They exist in your own experience in a way that may seem surprising, but which holds real depth. All the radiation you perceive, all the light entering your eyes, all the heat touching your skin, is the manifestation of temperature and emission processes identical in principle to what happens around a black hole. The sun warming your face is converting mass into energy through nuclear fusion, generating photons that took tens of thousands of years to emerge from the solar core and just 8 minutes to reach you. Every photon hitting your retina is a quantum of information that travelled from an energy source and was absorbed by your atoms, transferring a microscopic impulse and provoking a chemical reaction your brain interprets as vision. You're immersed in radiation. You're crossed by radiation. You constantly emit radiation in the infrared range by being at a temperature above absolute zero. You are, in your own way, a thermal emitter. The difference between you and an accretion disk is not one of kind, it is one of scale and organization. The same principles governing the emission of photons from a hot plasma at tens of millions of kelvins govern the emission of heat from your body. The same quantum physics describing the vacuum fluctuations near an event horizon describes the fluctuations of the fields permeating the space where you're sitting or lying right now. Physics has no borders of application. It holds here, it holds there, it holds in the depths of space where gravity deforms the fabric of reality. And when you realize this, when you feel that you are part of the same universe that produces plasma jets and Hawking radiation and luminous accretion disks, something changes in your perception of what you are. You're not outside the cosmos observing from afar. You are one of its manifestations, one of its ways of organizing matter and energy into patterns that process information and perceive themselves. And so the system seems to be in equilibrium. The black hole spins, the accretion disk feeds it with matter and illuminates it with radiation. The jets carry energy into intergalactic space. Hawking radiation imperceptibly drains into the vacuum. Everything seems stable, cyclical, sustained. The internal geometry organizes itself according to the patterns of accumulated entanglement. The holographic principle ensures that information is not lost but redistributed. There is an elegance in this stability, a feeling that things have found their place and will remain so long enough for us to contemplate them calmly. But this calm is superficial. This equilibrium is apparent, Beneath the surface of all this regularity, there is a tension that physics does not yet know how to completely resolve. A structural fragility hidden exactly at the point where the interior and exterior touch without touching, where the horizon divides what is from what can never be known. Beneath this surface of order exists something physics describes with a word that carries its own weight: instability. Not the trivial instability of a system that oscillates and returns to equilibrium, but something deeper, more compromising, an instability woven into the very definition of the event horizon. To understand why the apparent equilibrium of a black hole can dissolve into something much more violent, one must follow the thread connecting the internal geometry to the behavior of the matter that keeps falling, keeps spinning, keeps pressing from the outside while the internal structure accumulates its own silent tensions. The accretion disk is not a peaceful object. It is turbulent by nature, governed by magneto-hydrodynamic instabilities that scramble the magnetic field, redistribute angular momentum, and create fluctuations in the rate at which matter spirals toward the horizon. There are periods when the flow of matter increases significantly, feeding the black hole with much more energy than the average can sustain. In these moments, the disk heats beyond any temperature matter can maintain in radiative equilibrium. Radiation pressure overcomes the gravitational pressure, keeping the disk layers cohesive. The disk literally begins to inflate, to expand radially, to change geometry. What was a thin disk becomes a torus, a thicker, more turbulent, more chaotic structure, which radiates differently and interacts with the magnetic field in a way that further amplifies the instability. This process has a threshold. Below a certain accretion rate, the system operates relatively quietly, emitting radiation in an approximately constant manner, keeping the disk geometry within predictable parameters. Above this threshold, something changes in character. Physics calls this transition the Eddington luminosity, a point beyond which the pressure of the emitted radiation overcomes the gravitational attraction that would keep the gas falling. For a star, exceeding this limit means losing mass to space. For a black hole with an accretion disk, it means the disk completely reorganizes, and the released energy no longer flows smoothly into space as light, but begins to channel in much more dramatic ways. Relativistic jets, which in previous parts were described as energy transport channels, reveal here their more violent character. When the accretion rate rises and the magnetic field near the horizon is amplified by the increase in magnetized material reaching the black hole, the jets can intensify suddenly and extraordinarily. Instead of constant flows of plasma moving at high fractions of the speed of light, they become even more concentrated, even more energetic beams, carrying particles at speeds reaching 99/100ths of the speed of light. The apparent brightness of these jets, when viewed from favorable angles, can far exceed the luminosity of the entire host galaxy, creating what astronomers call quasars or blazars depending on the jet's orientation relative to the observer. What happens inside the horizon during these episodes of intense accretion is something physics predicts but cannot directly observe. The singularity, which under conditions of relative equilibrium represents a point of extreme curvature where Einstein's equations break down in a more or less static way, now receives a much larger influx of energy and information per unit of time. The internal geometry, which quantum entanglement and the holographic principle helped organize into something that perhaps had structural coherence, is now perturbed by this more intense arrival of matter. The interface between curved spacetime and the region of infinite curvature becomes more active, more dynamic, and the theoretical models trying to describe this state still diverge significantly from each other regarding what this means for the internal structure. One of the most dramatic consequences physics predicts for these episodes occurs not inside the horizon, but exactly in the region that exists between the event horizon and the ergosphere for rotating black holes. When the accretion rate increases greatly, the amplified magnetic field creates conditions for the extraction of rotational energy from the black hole. The Blanford-Znajek process, previously described as the mechanism feeding the jets, to become extremely efficient. The black hole begins to lose angular momentum at a much higher rate than under normal conditions. It is being braked by the very magnetic field that surrounded it, with the arrival of more magnetized matter. This braking has consequences. As the rotation decreases, the ergosphere contracts, the region of spacetime drag shrinks, and the entire geometry the ergosphere sustained around the black hole begins to reorganize. This geometric reorganization around the black hole in a phase of intense accretion emits signals that modern instruments can capture, although indirectly and always mediated by the physics of radiation emission. The high-energy X-rays emerging from the regions closest to the horizon carry spectral impressions reflecting the curvature of space-time. The ion emission line, which appears in many spectra of active galactic nuclei, is deformed in a very specific way by the gravitational field, broadened and distorted in a manner that allows inferring how close to the horizon the gas is emitting. When the system enters intense mode, this line distorts even more, broadens even more, revealing that the radiation is emerging from regions of more extreme curvature, that the geometry around the horizon has changed. X-ray observatories orbiting Earth, such as XMM Newton, Chandra and NuSTAR, spend years monitoring supermassive black holes in active galactic nuclei, trying to capture exactly these variations. When a system goes through an episode of elevated accretion, the X-ray luminosity can grow by a factor of hundreds in a matter of days or weeks, a change that for an object with the mass of millions or billions of suns is extraordinarily rapid. The analysis of the spectrum and temporal variability allows building models of the geometry around the horizon, indirectly mapping where energy is being released and how the magnetic field is structured. But the most dramatic phenomena do not come only from accelerated continuous accretion. Sometimes, what feeds a black hole is something much more sudden. When a star approaches a supermassive black hole too closely, tidal forces tear that star apart in fractions of its orbital diameter in a matter of hours or days. What was a star with a mass comparable to the Sun becomes a flow of hot gas spiraling toward the horizon in an event astronomers call a tidal disruption event. These events produce luminosity flares that emerge from the silence of black holes that previously had no accretion disk, illuminating horizons that remained dark, revealing the presence of the black hole to humanity for the first time. During a tidal disruption event, the black hole that was previously in relative rest, without enough material to shine, receives in a short time a mass comparable to that of a star. The internal geometry that was in its state of minimal organization, the structure that distributed entanglement sustained in something close to quantum coherence, is invaded by an enormous amount of new information in a very compressed time. What happens internally during this impact is completely inaccessible to observation, but theoretical physics suggests that the singularity receives a significant perturbation, that conditions near the inner horizon change drastically, and that the entire hierarchy of internal regions described in previous parts goes through a reconfiguration phase, whose exact duration and nature are not yet understood. What is observed externally during these events is extraordinary. The X-ray and ultraviolet flare emerging from the disruption event can continue growing in luminosity for weeks before beginning to decline. If the black hole has enough spin and the magnetic field organizes favorably, a relativistic jet can also emerge from a system that previously had no jet at all. These jetted disruption events are rare and violent enough to be detected in galaxies at distances of billions of light years, reaching Earth as radio signals that radio telescopes capture long after the visible light of the event has dissipated. humanity has developed networks of coordinated observatories exactly to monitor and respond to these transient phenomena. When an X-ray satellite detects a sudden flare from a galaxy that previously seemed quiet, an alert is automatically transmitted to ground and orbit telescopes that change direction in minutes to capture the event in multiple wavelengths simultaneously. This multi-messenger astronomy, which coordinates X-rays, gamma rays, radio waves, and, more recently, gravitational waves, represents humanity's attempt to indirectly reconstruct what happens in regions that can never be visited directly. Gravitational waves deserve special attention in this context of intense phenomena. When two black holes orbiting each other finally merge, the event produces a disturbance in spacetime that propagates outward at the speed of light and is detectable by instruments like LIGO and Virgo at distances of billions of light years. The gravitational chirp, that signal growing in frequency and amplitude before the merger and then silencing, carries information about the mass and spin of both black holes and about the exact moment of the merger. But what happens internally when two black holes merge, how the two horizons combine into a single larger horizon, how the two singularities, if singularities are entities with individual existence, meet and resolve into one. This physics cannot yet describe with equations that remain coherent throughout the transition. The resulting black hole from a merger oscillates, like a drop of water vibrating after absorbing another drop. These oscillations, called quasi-normal ring-down tones, are predicted by general relativity and arise from the geometry of the new horizon trying to find its equilibrium state. Each oscillation mode has a frequency and a damping rate that depend exclusively on the mass and spin of the resulting black hole. Detecting these oscillations in gravitational signals is a way to test if general relativity is complete, or if other theories of gravity predict deviations in these patterns. It is, in a sense, humanity listening to the black hole find its own shape, its own stable geometry, after an event that reorganized everything. While you rest somewhere distant by an amount of light years the human mind cannot easily visualize, one of these events may be happening right now, at this exact moment when breathing deepens and the outside world begins to recede. A star may be being torn apart by a black hole that remained silent for geological eras. Two black holes that orbited each other long enough for entire civilizations to rise and fall on planets around neighboring stars are completing their final spiral and merging into a single object with a cry of gravitational waves traveling in all directions. A relativistic jet that was previously moderate may be intensifying now, reorganizing the magnetic field sustaining it, accelerating particles to energies no human-built accelerator has managed to reproduce. These phenomena are not isolated in space, each occurring in its own bubble of influence, each black hole living its own history separate from the histories of all the others. There are connections between them, relationships of scale and causality that cross distances that seem impossible, and that physics is only now beginning to try to articulate coherently. The merger that just happened does not end anything. It inaugurates. The newly born object, still vibrating like a cosmic bell, struck with enough force to shake the very fabric of space, already begins to establish new relationships with its surroundings. The magnetic field inherited from the two predecessors is reorganizing around a new rotational geometry. The field lines that previously belonged to two distinct centers now need to find a lower energy configuration, and this process is not instantaneous. It takes time, it takes perturbations, it takes reorganization waves propagating outward through the accretion disk, altering pressures, changing the trajectories of particles that were already in motion for decades of external time. The main energy exchange partner of a black hole in an active galactic environment is not another black hole. It is the accretion disk, that flat spiral structure of gas and dust orbiting in concentric layers, each layer at a slightly different speed, creating friction between them, and from this friction heat is born, and from this heat light is born. The disk is the universal intermediary. It receives matter from the environment, converts part of the gravitational energy of that matter into radiation, delivers part of that energy back to the magnetic field sustaining the jet, and returns the rest to the black hole in the form of mass crossing the horizon. This exchange is not passive. It is a high-voltage conversation where every departure of energy in one direction demands a response in another. When the newly formed black hole begins to stabilize its rotation, the disk around it perceives this change as a new internal boundary. The region closest to the horizon, called the innermost stable orbit, shifts slightly depending on the Kerr parameter, that quantity measuring how much space-time is being dragged by the rotation. A faster spinning black hole pushes this innermost orbit closer to itself, which means more gravitational energy can be extracted before the matter definitively falls. In practical terms, this means a faster spinning black hole is a more efficient engine. It converts a larger fraction of the mass it accretes into pure radiation before absorbing it. Calculations show that a non-spinning black hole converts about 6% of mass into energy, while one at maximum rotation can reach 42%. This, in energetic terms, is the difference between a candle flame and a fusion reactor. This efficiency differential has consequences that propagate to timescales we can barely name with comfort. In the short term, decades of human observation, what we see is relatively stable. An active galactic nucleus in a state of moderate feeding presents a luminosity that fluctuates, but within certain recognizable bands. We can monitor its emission in radio, in X-rays, in high-energy waves, and observe oscillations that sometimes last hours, sometimes last years. These oscillations are echoes of the disk, variations in the rate at which matter falls, pockets of denser or rarer gas reaching the central region and temporarily altering the system's brightness. In decades, the system seems to breathe with an irregular but identifiable rhythm. In centuries, the perspective changes. The reservoir of gas available around a central galactic black hole is not infinite. It depends on how the galaxy continues to feed this central region, either through mergers with smaller galaxies bringing fresh gas, or through internal instabilities pushing material from the edges to the center along spiral arms. If none of these replenishment sources are active, the disk progressively becomes scarcer. In centuries, this might not be noticeable, but the process is happening slowly, and the long-term fate of an unfed black hole is silence. In millions of years, what was a bright quasar may have transformed into an almost inactive galactic nucleus, an object emitting only a minuscule fraction of the luminosity it had when in full activity. The Milky Way itself went through this process. Sagittarius A star, the 4 million solar mass black hole inhabiting the center of our galaxy, is today an extraordinarily quiet object compared to what it probably was billions of years ago. There is evidence in the structure of our galaxy, gamma-ray emission bubbles called Fermi bubbles extending above and below the galactic plane, that at some point in the distant past Sagittarius A star had a much more intense episode of activity. Something happened. Enough gas fell onto it at once to ignite a jet or create a burst of radiation that left this gigantic signature etched into the structure of the gas around the galaxy. This episode happened so many millions of years ago that no biological eye was here to witness it. The light from that activity traveled beyond the galaxy, scattered into intergalactic space, became part of the radiation background filling the universe. The black hole that caused it is the same one that exists today, but now it is at rest, waiting for the next sufficiently substantial meal to awaken it. The civilizations that might have existed on planets around nearby stars during that episode would have seen, in what for them would be the center of the night sky, an unusual glow. A brighter point of light, nothing more. The violence of the process, the nature of the horizon, the singularity inside were invisible. only the glow, only the consequence that escaped. Sensitivity to initial conditions is one of the most unsettling aspects of black hole physics applied to real systems. Small differences in the parameters of an accreting system can lead to radically different behaviors over time. Disk physics, with its turbulent flows of magnetized plasma, is inherently chaotic in the technical sense of the word. That sense where small variations in input conditions amplify exponentially and produce outputs impossible to predict accurately beyond a certain temporal horizon. A black hole with an accretion disk almost identical to another's, but with a slightly different magnetic field concentration in a critical region, can produce a jet that is 10 times more powerful, or that completely collapses, or that precesses at a different angle, altering which regions of the galaxy are irradiated. This is not a flaw in science, it is a characteristic of the universe. The fundamental limits of prediction are not just technological, a matter of insufficient precision in instruments or models. They are partly epistemic. There is information about the internal state of an accreting system that is simply unavailable to an external observer because it is encoded on scales below those we can resolve, or because it is protected by the event horizon and therefore literally inaccessible by definition. When we try to build predictive models for how a black hole will behave in the coming decades, we are building an incomplete map of a territory that deliberately hides part of its own structure. And yet, the models work. Not perfectly, not with the precision of a clock, but with a kind of statistical accuracy that is, in itself, a form of beauty. We can predict that a certain class of accreting black holes will produce jets with certain properties. We can predict that the merger of two black holes of known masses will produce gravitational waves with a characteristic temporal profile. We can predict that a quiescent black hole in a spiral galaxy, perturbed by a close passage with another galaxy, will have its accretion rate increased within a predictable time frame. These predictions, when confirmed by observation, produce a satisfaction that is not merely intellectual. Something deeper is happening in this moment when the universe answers the questions we ask it. The beauty of a system that is simultaneously comprehensible and surprising lies exactly in this tension. If black holes were simply strange and opaque, inexplicable in all their aspects, we could not do science with them. They would be philosophical curiosities, objects of speculation without an anchor. If, on the contrary, they were completely predictable, simple systems obeying rules without exception or surprise, they would be interesting only as examples of well-behaved physics. What makes them truly fascinating is that they inhabit the boundary between these two extremes. They are sufficiently regulated by mathematics for us to speak of them with precision, and sufficiently rich in emergent behavior for every new observation to carry the possibility of revealing something we did not predict. The gravitational waves that the recent merger emitted are now propagating through the cosmos. They do not transport matter, they transport information about the geometry of spacetime at a specific moment, a fingerprint of the event that generated them, encoded in oscillations traveling at the speed of light that weaken with distance but never completely disappear. If there is someone somewhere sufficiently distant, with sufficiently sensitive instruments, they may one day receive this signal and reconstruct, from the ripples in the fabric of space, what happened here. They will know that two black holes collided. They will know approximately their masses. They will know how long the event lasted. They will know nothing of what is inside the horizon, but they will know the event happened. There is something almost moving about this transmission. The universe records its own events in a medium that is space itself, and transmits these records in all directions without a specific recipient, like a message sent to anyone willing and equipped to listen. All the physics of black holes, all the complexity of the accretion disk and the jet and the horizon and the singularity and the gravitational waves, is in a way an elaboration of this simple act. The universe happens, and by happening, it announces itself. The rhythm of all this, when we step back far enough to see the full picture, begins to feel different. The decades of human observation are a minuscule fragment of the timescale on which black holes operate. The cycles of accretion and quiescence of a central galactic black hole unfold on scales of tens of millions of years. The evaporation time of a black hole through the Hawking emission process for objects of stellar mass or larger far exceeds the current age of the universe. We are looking at objects that exist in a different time than ours, a slow and vast time in which what we call human history is an imperceptible pulse. And yet within this slow time, something persists. There is a constancy in the principles governing these objects, a regularity that spans all scales and all environments. A black hole in a distant dwarf galaxy obeys the same equations as a black hole at the center of a quasar billions of light years away. The curvature of spacetime, the conservation of angular momentum, the relationship between mass and Schwarzschild radius, the emission of radiation by accelerated particles, all this repeats with extraordinary fidelity in every system we study. Beneath all the complexity, beneath the richness of emergent phenomena and chaotic behaviors and interactions between scales that sometimes seem impossible to reconcile, there is something uniting all these systems. It is not just gravity, although gravity is the most visible thread. It is something even more fundamental, something physics is still learning to name correctly, something connecting the behavior of the horizon to the behavior of the singularity, to the behavior of the disk, to the behavior of gravitational waves, and to the nature of space and time themselves. A unity that is there, waiting to be recognized with the clarity with which we recognize, upon waking from a deep dream, that what seemed fragmented was actually a single thing seen from different angles. The unity physics pursues is not just an aesthetic convenience, a human preference for order in the face of chaos. It is inscribed in the structure of reality with a depth that goes beyond what any individual equation can capture. When we look at a black hole not as an isolated object, but as a living system of feedbacks and dynamic equilibria, we begin to realize that the horizon is not a boundary between the known and the unknown. It is the place where the universe folds back upon itself in a way that reveals its own foundations. There exists within any system orbiting a black hole a dance of feedbacks that sustains and amplifies and sometimes destroys. The accretion disk, for example, is not a static structure. As matter spirals toward the horizon, it heats up. By heating up, it radiates. By radiating, it loses energy. By losing energy, it gets closer to the center of gravity. By getting closer, it moves faster, and the speed produces even more heat through friction and compression, and the heat produces more radiation, and the radiation exerts pressure on the gas still trying to fall. At certain moments, this radiation pressure is enough to expel part of the matter away, forming winds and jets traveling at considerable fractions of the speed of light. The black hole, by swallowing, also expels. By absorbing, it also radiates. By growing, it also resists its own growth through the pressure its hunger generates. This feedback is not instability, it is regulation. It is the universe finding a path between two extremes, between total collapse and total dispersion, and maintaining for some time an intermediate state where matter can orbit, accumulate, shine, and eventually fall. Physics calls this state radiative equilibrium, but the word equilibrium does not quite capture the dynamic tension existing there. It is less like a still lake and more like a waterfall, where the water falls continuously, but the shape of the fall remains for some time recognizable. On the other side of this dynamic exists an amplification feedback that can become catastrophic. When two black holes approach each other, the space between them begins to curve in ways that accelerate the process. The curvature produces forces bringing them closer, and the approach produces more curvature, and at a certain point the system reaches what is called orbital instability, where no stable orbit is possible anymore, and the two objects plunge toward each other in a final spiral. During these last instants, the amount of energy released in gravitational waves is greater than the combined luminosity of all stars in the observable universe for a fraction of a second. The universe screams in geometry before settling back into silence. The deepest dimension of a black hole is not the singularity at its center, although the singularity is where the limits of current physics become most evident. The deepest dimension is compositional in the most fundamental sense possible. A black hole is made of space and time folded upon themselves with such intensity that the distinction between the two disappears. Outside the horizon, space and time are different directions. You can choose to stand still in space while time moves forward. You can move in space in any direction. But inside the horizon, the direction pointing toward the singularity becomes so much like a temporal direction that moving toward it ceases to be a choice and becomes a necessity. Just as you cannot go to the past, you cannot stop going toward the singularity. This means the matter inside the horizon is not composed in the same way as matter outside. It is not a matter of temperature or pressure or density. Although all these parameters reach values defying any human intuition, it is a more fundamental question. The matter crossing the horizon enters a region where the very categories of space and time, organizing our understanding of structure and composition, cease to apply in the usual way. The quarks forming the protons, forming the atoms, forming the star that collapsed still exist, presumably, but they exist in a substrate where the concept of simultaneous position loses the same meaning, where what we call here and now intertwine in ways no established physics describes precisely. Quantum physics adds another layer to this deep composition. Every particle that exists has a wave nature, and waves do not have a defined position. They spread out. On normal scales, this imprecision is negligible, but near the singularity, where scales compress to the point where space-time geometry fluctuates significantly, quantum imprecision and gravitational curvature meet. It is the place where quantum mechanics and general relativity, the two great theories describing the universe at its extremes, are forced to coexist without an established common mathematical framework. What exists there is neither particle nor wave nor pure curvature. It is something awaiting a description yet to be written. When we look at a black hole as an integrated system, what emerges is a structure with layers of organization communicating with each other in non-intuitive ways. The accretion disk feeds the horizon. The horizon feeds the system's thermodynamics. Thermodynamics determines Hawking radiation. Hawking radiation slowly subtracts mass from the black hole. The subtraction of mass alters the horizon's curvature. The alteration of the horizon affects the orbits around it. The orbits determine the accretion pattern. The accretion pattern feeds back into the disk. It is a closed system of mutual influences, a cosmic organism existing for billions of years in a state of sustained dynamic tension. The relativistic jets emerging from the poles of some black holes are the most visible expression of this systemic integration. They do not arise from the horizon itself, but from the region immediately above it, where the magnetic field of the accretion disk twists and concentrates through the black hole's rotation, through the space dragging effect known as frame dragging. The black hole spins and carries space with it, and the carried space squeezes the magnetic field lines as if they were twisted fibers in a rope, and this concentration creates a channel where particles are accelerated with extraordinary efficiency. The jet is the universe using space-time geometry as a particle accelerator, something no human engineering has managed to replicate on a comparable scale. The emergence of complex patterns from simple rules is perhaps the deepest lesson black holes teach. The rule is simple: mass curves space-time. Curvature determines how everything moves. Everything moves according to the curvature it itself, and everything around it creates. From this single idea emerge accretion disks with laminated structure, jets traveling for millions of light years without dispersing completely. Gravitational waves carrying information about collisions occurring at unimaginable distances, horizons that have temperature and entropy and thermodynamic behavior, singularities where space and time end or transform into something yet unnamed. The simplicity of the rule and the complexity of the result are not in contradiction. One is the necessary consequence of the other. Deep down, a black hole is simply the universe taking gravity to its logical conclusion. It is what happens when the curvature of space-time becomes so intense that it itself becomes the only relevant reality, erasing all other forces, all other structures, all distinction between directions, all meaning of distance and duration as we know them. The horizon is the place where the logical consequence becomes visible as a boundary. The singularity is the place where the consequence completes itself beyond the reach of current mathematical language. The disk and the jets and the gravitational waves are the surrounding universe reacting to this conclusion, perturbed and organized and transformed by the presence of that which can no longer be undone. Every element we explored throughout this night connects to this central principle. The curvature of space-time, which we explored when talking about how geometry changes around the horizon, is the simple rule in action. Time dilation, which makes a distant observer see time almost stop for someone approaching the horizon, is the curvature manifesting in the experience of time. Hawking radiation is quantum mechanics refusing to let the principle of curvature operate without consequences for the black hole itself, insisting that even the most absolute of objects must participate in the energy exchange characterizing the quantum universe. The area theorem, stating that the horizon area can never classically decrease, is thermodynamics recognizing that the logical conclusion of gravity has an entropic nature, that there is a fundamental irreversibility in gravitational collapse, echoing the irreversibility of heat flowing from hot to cold. Gravitational waves are the universe propagating information about this process, sending ripples through the fabric of space-time, reaching us as whispers of events occurring in depths and distances we can barely imagine. Everything is gravity taken to the end, everything is space-time curving upon itself. Everything is the simplest rule of the universe producing the most extreme reality the universe contains. And now, with this unity recognized, something changes in the quality of the silence. The universe is much larger than any anxiety that might exist at this moment. Black holes spin at the centers of galaxies with a patience exceeding any human scale of concern. They existed before there were eyes to observe them. They will exist when the universe is much older and colder and darker than it is now. And at this exact moment, while you rest, each of them continues its silent work of curving space, of accumulating matter, of slowly radiating the history of the universe in faint radiation traveling immense distances without hurry. You're safe. The universe takes care of you with the same consistency with which it maintains the laws of physics operating in every corner of the observable cosmos. The gravitational constant making an apple fall is the same keeping galaxies in orbit around each other. You're within these laws, you're protected by them. You do not need to do anything to deserve this protection. It already exists. Everything is in order. The processes sustaining life on this planet, the rotation bringing the morning, the magnetic field deflecting the solar wind, the temperature keeping water liquid, continue happening with a regularity that does not depend on your waking state. The universe does not need you to stay awake to keep functioning. It functioned for billions of years before you existed. It knows what it is doing. While you rest, black holes continue curving the space around them with the same serene inevitability as always. The accretion disk of the nearest galaxy continues spinning, heating, shining in wavelengths no human eye sees directly, but which exist with all the reality of anything visible. The gravitational waves from collisions happening before the sun existed continue propagating through space, passing through you now, moving the fabric of space-time by a fraction of a proton, imperceptible to the body but real to physics. You're immersed in this. You are part of this. The matter composing your body was formed in stars that existed and died before the sun was born. Some of those atoms passed through regions near black holes in unimaginably distant epochs. They carry this history without knowing it. You carry it without knowing it. There is a continuity between what you are and what the universe is that goes far beyond any metaphor. It is literal. It is physical. It is real. You have always been part of this. The event horizon exists right now somewhere in the universe, perhaps in many places, perhaps in millions of places, each curving space with absolute silence. No sound crosses the vacuum between stars. The cosmos is fundamentally silent, and this silence is not absence. It is the background texture of everything that exists, the natural state of the universe when there is nothing disturbing its serenity. You can rest in this silence. Let the thoughts still circulating find their natural orbits, like matter eventually stabilizing into orbits around a gravitational center. There is no need to solve anything right now. The universe will wait. The questions will wait. Sleep is one of the oldest things there is. Older than humans, older than animals, present in some way in almost all life that has ever existed on this planet. Your body knows how to do this. You just need to let it. Close your eyes a little more. Imagine the event horizon as an absolutely calm surface, a perfect sphere in the dark of space, without waves, without visible disturbances, just the quiet presence of something existing beyond any agitation. This calm is not indifference. It is the deep stability of something that has reached its essential form. You too can reach your essential form now. The universe continues its silent dance, and we rest in its embrace. Thank you for walking with me tonight. Sleep well.